when we try to graph some curve. نحاول نسوي رسمة some curve thanks to what you have in our hand. That means what we know like increasing, decreasing, inflection point, maximum, minimum, and symmetry, and something like. First of all, we have to know to have idea about the domain. It's very useful to know what is the domain of the function. The domain, that means the x values such that f of x is defined, just defined. This is about the domain. The second information useful is to know the intersection between the y-intercept and the x-intercept. That means we have to solve x equals 0 and to evaluate f of 0. First of all, this is the y-intercept, and after that we have to solve f of x equals 0, which is f of x equals 0. That means y equals 0. This is the x-intercept. Then second step, after the domain, we have to know the y-intercept and the x-intercept. That means to evaluate f of 0 and to solve x that f of x equals 0. The third step is to know if we have some symmetry. Some symmetry, that means if f of minus x equals f of x, in this case we have symmetry related to the y-axis, as you know. If we, because we have an even function, if we have an odd function, we have a symmetry. This is an even function. That means when we have idea about the graph in the right side, then we can conclude the graph in the left side. Right side, that means in the right of 0. That means when we have idea about the graph, if x is positive, then we can have idea about the graph in R. That means when we know just the right side, this is the right side, it's here. Okay, this is the right side. The left side, we can conclude the left side thanks to the symmetry, because you know we have a symmetry related to the y-axis. That means your function is symmetric related to the y-axis. This is true when we have an even function like x squared, x to the 4, absolute value of x, and cosine x, for example, and more general for any even function. This is if we have an odd function, then we have the same, we can conclude the left side thanks to the right side. Odd function, that means f of minus x equal negative f of x. Like sine, like x to the 3, like x, like in this case, we have a symmetry related to the origin. That means your graph is symmetric related to the origin, like x, x to the 3, x to the 5, sine x, and so on. Sometimes we have a periodic function like cosine and sine. That means we have a period f of x plus p is equal f of x. Obviously, if it's sine and cosine, p is equal to pi. If it's tan, p is equal pi just. Then sine and cosine have a period, has a sine has period 2 pi. The same thing for cosine. Tan has just as period pi. Okay, it's known, and we did this last. But now, for me, just I have to remember when we have an idea about the graph of the function in any interval, then we can do the same action in the interval before and after. This is the main important point for today. Then to summarize, we have the domain, the x-intercept, the y-intercept, and the symmetry. The next point is about asymptote. We have to evaluate limit when x goes to infinity. If this is a capital L, then y equals L is an horizontal asymptote as we studied in chapter 2. Okay, that means here if this limit is equal capital L, that means when x is large enough, your function is small to capital L. We have this situation, we call it, we have an horizontal asymptote. If the limit is equal infinity, then we don't have any asymptote, but we have an idea about that means your function becomes large enough when x is large enough. Okay. If in any point, we studied this in chapter 2, if we have in any point as limit infinity, then we have a vertical asymptote. Okay, this is if the point is finite. This is maybe all related to, obviously it's important to know if the limit is infinity or infinity, and if it's in the right side or in the left side. That means if it's in A plus or A minus. Okay. Another thing is to have idea about the monotony. That means if your function, in which interval the function is increasing, decreasing, something like that, and if we have a maximum, local maximum, minimum, maximum, okay, and at what time the derivative, the sign of the derivative changes. This is maybe all these items. We can use all these items in order to draw your function. Obviously, the concavity in order to know the inflection, and the point of inflection in order to know if your concavity, if your function is concave upward or downward. Obviously, if it's upward, بمعنى it's something like that. It's something like that. But if it's downward, it's something like that. That means here the curve look down, however here the curve look up. This is all. We have a lot of things useful in order to graph the function. We studied all before, and in order to graph your function, we use this. This is a video. I don't know if we can see the video together.
Okay, in this video, we're going to do a summary of curve sketching. There's a lot of things to discuss in this. We're going to talk about domain, x and y intercepts, symmetry, horizontal and vertical asymptotes, intervals of increase, decrease. We'll try to find any local maximums and minimums. We'll talk about concavity and points of inflections, and then try to do a rough sketch based on that. There's a lot of stuff here, so this is going to be part one of at least 2 parts of the video, so definitely won't be able to finish it all out in this one. The first thing we want to discuss is the domain. And for this particular type of function, it's a rational function. And again, for a fraction in general, you don't want to be dividing by 0. So it looks like the only value that would be excluded from the domain of this function would be the value of x that makes the denominator 0. So that's what I'm doing, simply setting the denominator equal to 0. So if you saw in this case is going to be from negative infinity to 0, and then from 0 to infinity. Notice the parentheses on the 0. Again, just emphasizing that in fact we cannot use it. To find x and y intercepts, remember to find the y-intercept.
Then here, step 1, he evaluated the domain related to the function. We have a denominator, and sometimes the denominator is equal 0, because here we divide by x squared. Then just be careful at what time x squared equals 0. If it's r without 0. It's intercept and the y-intercept. Let's
we plug in x equals 0. But, well, we just said we can't use x equals 0 because it's not in the domain. So what that means is, well, then there's no y-intercept for this graph.
Y-intercept, that means x equals 0. Here, obviously, just in the step before, we said no, we cannot use x equals 0 because in 0 is not defined. That's why no intersection with the y-intercept.
Simply not going to cross the y-axis. That's okay. To find the x-intercepts, we set y equal to 0. So then we'll have to solve 0 equals x minus 1 over x squared. For a fraction to be 0, the top part has to be 0. So really all we have to do is set x minus 1 equal to 0. And
here we have a fraction, and then x minus 1 over x squared equals 0. That means x equals 0. This is the x-intercept.
Then we'll get x equals 1 being our x-intercept. Okay, so we need to keep that guy in mind. Next, let's do symmetry here. So I could label this function instead of y, I could call it f of x. So remember for symmetry, let's see if I can squeeze it down here. For symmetry, remember the rule says if f of negative x equals f of x, it's symmetric about the y-axis. And it says if f of negative x equals negative f of x, then it's symmetric about the origin. So we're going to use this little test just to see whether or not our function is in fact possessing any symmetry. So it says f of x is x minus 1 over x squared. So if I plug in negative x, I'm going to get negative x minus 1 over negative x squared. And if you simplify that down, you simply get negative x minus 1 over x squared. Again, just based on this definition of symmetry, it says if you plug negative x in and you get the exact original out, it's symmetric about the y-axis. Well, I don't think we got the exact original thing out because notice the original x.
إذا ما في واضح هنا try to evaluate f of minus x. طبعا يقول انه ما وجدها لا f of x لا f of minus 6 as we are going to.
X was a positive and this one's a negative. The other condition says basically if you get the negative of the original, then it's symmetric about the origin. But also it's not the negative of the original. Imagine factoring the negative out of the top. You would get x plus 1 over x squared. And again, that's not the negative of the original because the sign on the 1 is a plus 1 instead of being a minus 1. So the conclusion of the story is that there's simply no symmetry. Okay, so the next thing we'll do is we'll talk about asymptotes. And remember for rational functions, you're going to get a vertical asymptote basically where the denominator is 0, but the top simultaneously has to be not 0. Okay? So if you look at our function, we already said that x equals 0 makes the denominator 0. Well, it certainly doesn't make the numerator 0. Imagine plugging in 0, you get negative 1 over 0. Again, we're getting this little property that we have a number that's not 0 divided by 0. For rational functions, that implies that the line x equals 0 is a vertical asymptote. The next thing we would have to do is find any horizontal asymptotes. And remember to find horizontal asymptotes, you look at the limit as x goes to positive infinity, and then you also look at the limit as x goes to negative infinity. But again, for rational functions, it turns out you can do them simultaneously. If the limit on one side exists, the limit on the other will exist, and will be the same number. There's a trick for rational functions. It says if the power on bottom, the degree of the polynomial on the bottom is bigger than the degree of the polynomial on top. In the denominator, we have a polynomial degree 2. On the top, we have a polynomial degree 1. It says that this limit will always work out to be 0. And I do these in another video talking about limits at infinity, and I believe for rational functions even. So this says that the line y equals 0 is going to be a horizontal asymptote. So we'll have to use that when we sketch our graph, obviously. The next thing we need to figure out are intervals of increase and decrease. So to find intervals of increase and decrease, we're going to have to take the derivative of our function and figure out, do our little sign chart and figure out, again, where the derivative is positive and where the derivative is negative. So it looks to me like if we take the derivative, we're going to have to use the quotient rule. So the quotient rule says you get the bottom times the derivative of the top, which will just be 1, minus the top, make sure you put that in parentheses, times the derivative of the bottom, which would be 2x, all over the denominator squared. Okay, so we need to clean this up a little bit. It looks like in the numerator you get x squared. We'll get x times 2x, which is 2x squared, but we have to distribute the negative, so we'll get negative 2x squared. Negative 1 times 2x is negative 2x, but again, we'll have to distribute the negative and make it positive 2x. We get x to the 4th on the bottom. If we combine our like terms, it looks like we get negative x squared plus 2x over x to the 4th. So now all I'm going to do simply is factor an x out of the numerator just to clean things up. And it looks like we'll have negative x plus 2 over x to the 4th. My x on top will cancel out with one of the x's on the bottom, leaving me with just x cubed. And I'm going to rewrite that thing now as just 2 minus x, just because I want it. Just I think it looks a touch better that way. So at this point, we have to make our little sign chart. Remember, we have to find the critical numbers of the first derivative. Technically, you just want to look basically where the first derivative is undefined and where it equals 0. Well, it's going to be undefined when the denominator is 0, which is 0. The numerator is going to equal 0 when x equals 2. And again, now we have to take numbers. Notice if you take a number between 0 and 2, say 1, if you plug it into the function, the derivative is going to be positive over that interval. That means the function is increasing on that interval. If you take a number larger than 2, okay, well, the numerator is going to be negative. The denominator is still positive. So that means the function is decreasing after 2. If you take a negative number, say negative 5, well, the numerator is going to become positive, but the denominator will become negative. So that means the function is decreasing. So now we know that our function f is increasing on the interval 0 to 2, and it's going to be decreasing on the interval negative infinity to 0, and then from 2 to infinity. From this, we automatically get that we have a local max at x equals 2. If you plug 2 into your function, it looks like you'll get 1/4. So we have a local max at 2, 1/4. It looks like, our function goes from decreasing to increasing, but remember 0 is not even in the domain. So there's no way that 0 could correspond to a local minimum. All right, so we're getting close. This is part 1. I'm going to finish out concavity, inflection points, and actually sketching it in part 2 of this video. So dig around, it should be close. All right, this is going to be the continuation of the curve sketching problem. So I think we just finished off figuring out where the function's increasing, decreasing. Again, that helped us find local maximums and minimums. Part G said you want to figure out the concavity and any inflection points. It's almost an exact repeat of what you did in step F. So now we have to take the derivative of the first derivative. So again, it says you get the bottom part times the derivative of the top, which will just be -1, minus the top part times the derivative of the bottom part, all over the bottom part squared. All right, so again, you're going to want to clean this up. So the top, it looks like you get negative x cubed. Again, if you FOIL out, you'll get 2 times 3x squared, which is going to give you 6x squared, but the negative is going to make it, well, negative 6x squared. If you distribute the negative x, you'll get negative 3x cubed, but then it'll become a positive 3x cubed. In the denominator, x cubed squared will give us x to the 6. You just multiply. Combine your like terms. It looks like we've got negative 1x cubed, positive 3x cubed. That's going to give us 2x cubed minus 6x squared over x to the 6. Just like our last problem, we'll factor out anything we can from the top. Mainly, I'm going to factor out an x squared. Looks like we'll be left with 2x minus 6 over x to the 6. And this will simply give us, we could even factor the 2 out, and then be left with x to the 4th. Okay, so that's what I got here for my second derivative. And again, now we basically just need to do the same thing that we did before. We only call them critical numbers for the first derivative, but you still make this little sign chart for the second derivative and do the same thing you did a second ago. So I think what value will make the numerator 0? Well, how about x equals 3? What value would make the denominator 0? How about x equals 0? Same thing. Notice if we take a number between 0 and 3, maybe we can use 1. It looks like the numerator is going to be negative. The denominator is going to be positive. So the sign's negative, and that means it's concave down on that interval. If we take a number, say, smaller than 0, say negative 1, it looks like the numerator is going to be positive. The denominator will be positive. The sign is positive. That means the graph is going to be concave up on that interval. Take a number bigger than 3, say 4. The numerator will be positive. The denominator is always positive. So again, we're going to get positives, and that means it's going to be concave up on that interval. Again, an inflection point is a point on the graph where the concavity changes. Well, again, it looks like it changes concavity at 0, but you have to remind yourself that 0 is not even a point. The function's undefined at 0, so that cannot be an inflection point. So let's see. So the inflection point corresponds to the x coordinate of 3. And again, if you think about the original function, x minus 1 over x squared, if you plug 3 in, what are we going to get out? It looks like 2 over 9. So it says our only inflection point will be at the point 3 comma 2/9. And now I think we have just about everything we need to sketch a nice little graph here. Let's see if we can't put it all together. So I was looking for one of my other pieces of paper where I had everything written down. So these are long problems, and unfortunately, I think a rational function is maybe a touch one of the. They're not completely miserable. They're definitely long. Some of the other ones can be pretty tricky, I think. On a test or a quiz, I always ask people to do rational functions because they have vertical asymptotes, they have horizontal asymptotes, so you have to do limits. To me, these are kind of good problems. So if you have curve sketching coming up on a test or a quiz, I would definitely study at least 1 or 2 rational functions, but obviously don't limit yourself to those. Okay. Well, we said y equals 0 was a horizontal asymptote. We said x equals 0 was a vertical asymptote, so there are those points. We said that at x equals 1, that was our x-intercept. Our local max was at 2 comma 1/4. So I'm going to put it up here a little bit. And then over here at 3 comma 2/9, we're going to have our inflection point. And let's see, now if we can't make everything, just do what it needs to do. So We know that x equals 0 is a vertical asymptote. Notice if you start taking numbers that are close to 0 but negative, what's going to happen? I mean, even take a number to the left of 0. Maybe you plug in -4. It looks like you're going to get a negative number out. So our graph is definitely below the x-axis. Since there's no other x-intercepts, that means the function has to stay strictly below the x-axis. So that I know that when it approaches this vertical asymptote of x equals 0, it's going to have to be decreasing there. And I'll just make it approach that horizontal asymptote. So notice we're trying to make it close to this line y equals 0, which makes it a horizontal asymptote. Our graph is concave down and decreasing, so I think that part should be okay. It looks like our function was concave down from 0 to 3. The function was increasing up to 2, so I'm going to try to make it increasing up till 2. It's supposed to have this concave up shape to it. It's supposed to kind of look like the left side of a parabola, kind of like that. And then we know it's still concave down, I think I said concave up. It's concave down from 0 to 3, so it still should have this kind of parabola shape. But we said from basically 2 to infinity, the function keeps decreasing. And we said from 3 to infinity, the function becomes concave up. So now it's going to have this concave up shape, but again, it's approaching this horizontal asymptote. So your graph should look something roughly like that. All right, so again, maybe not the most beautiful artistic rendition. Hopefully I didn't misspeak too many times there. This should definitely be the correct graph. Play with it. If you're having troubles, I would say pause it at the very beginning. Maybe it's too late now. Pause it at the very beginning. Try to work it out on your own. You can always compare your stuff to what I have here. If you need to see some other videos, feel free to visit my website.
صوت واضح الحين؟ You hear me?
الصوت واضح.
إذن طبعا الفيديو هذا موجود على اليوتيوب. You can see it once again. But it's just an example. In practice, the kind of example when we ask is about fractional function. That means polynomial divided by another one. This is another example. I'll do it quickly. Here, this is the function. It's 2x squared divided by x squared minus 1. Now, the first step is to evaluate the domain. The domain, that means at what times the denominator is equal 0. That means the denominator is equal 0, obviously just 1 and -1. That's why the domain is R without these values, اللي هما 1 or -1. Is it clear right now? Step 2, what is the x-intercept and the y-intercept? Okay. When x equals 0, f of x equals 0, and when y equals 0, then x equals 0. That's why the x-intercept is the x-axis and the y-intercept is the y-axis. Then both are 0. That's why he said the x-intercept and the y-intercept. For the symmetry, here we try to evaluate f of -6. When we evaluate f of -6, we can remove minus without any problem. After just some simplification, that's why your function is even function. Then try to, then the function here is an even function because f of -6 equals f of x. The next step is to evaluate the limit in infinity, plus or minus. Here, the limit in infinity is equal to, you can use Hospital's rule, or you can see when we have a fraction or polynomial divided by polynomial, when we are close to infinity, the higher power is the main important thing. Then here we have 2x squared, and in the denominator we have x squared. That's why the limit equals then when the limit equals 2, when the limit in infinity of f of x equals 2, then y equals 2 is a horizontal asymptote. Related to the vertical asymptote, at what time you have some problem in the denominator? We have problem in 1 and -1. That's why we try to evaluate the limit in 1 plus and 1 minus, and in -1 plus and -1 minus. بالنسبة للموضوع هذا, in general we have something, when we have something positive like 1, 2, 3 or any y, divided by infinity, by something small enough. Positive divided by small positive. Be careful, the sign is important. بمعنى we have to know what is the sign of the expression small positive. For example, when we have positive divided by small positive, then the limit is plus infinity or infinity. When we have negative divided by small negative, the limit also is infinity. When we have negative divided by small positive, the limit is negative infinity. Then, first of all, when we have some constant divided by small, the limit is infinity. In order to know if it's a plus infinity or negative infinity, we have just to know the sign of your expression. Here, for 1 plus, this is 1, this limit, this terms go to 2 anyway. However, in 1 plus, x squared minus 1 is positive. That's why 2 divided by something small is infinity. Here, 2 by something small positive is infinity. However, here, 2 divided by something small negative is negative. And so on. Then we have this 4 limit. Now it's time to draw the graph maybe, because we have all the requested. Now we have -1 and 1 as a vertical asymptote. We have 2 as horizontal asymptote. This is what we have. Now we will move to know at what time it's increasing, at what time it's decreasing, which is done here. This is the derivative. Obviously, we use the derivative of a fraction is equal when we have f equals h over g, then f prime is equal, you know the expression of f prime, من يقول لي كم اشتقاق القسمة، قانون القسمة، f prime is equal what? f prime is equal h prime g minus h g prime divided by g squared. H prime g minus h g prime divided by g squared. Then, thanks to this formula, h is equal the numerator and the g is equal the denominator. When we apply this formula, this is the derivative. Obviously, when we look about the denominator, it's positive when it's defined. However, the denominator is negative if x is positive, لأنه هذا ما عنده مشاكل بالنسبة للدenominator. It's positive anyway لأنه تربيع. However, the denominator is positive if x is negative, and it's negative if x is positive. Then your function is increasing here in the left of 0 and is decreasing between 0, 1 and 1 infinity. We have just one critical number, which is 0. Obviously, we have 0 as critical number because the function is not defined in 1 and -1. Okay. Then in 0, the derivative change from positive to negative. Then we have a local maximum. Why? Because the derivative in the left of 0, your function is increasing. In the right is decreasing. That's why 0 is a local maximum. Maybe now it's almost done. This is slide 20. In slide 21, we have finally to evaluate the second derivative. When we evaluate the second derivative, it's like that. This you have to know at what time it's positive and at what time it's negative. Now the numerator is positive because 12x squared plus 4 is positive, And this one, it's equals 0 in 1 and minus 1. Then it's positive in the right of 1 and the left of minus 1. كيف الطريقة؟ قلنا احنا ناخذ 1 minus 1 1 okay minus 1 and 1. Here we have some important point not included in the domain minus 1 and 1. And we try to evaluate the sign of the second derivative. It's positive here and here. However, it's negative between minus 1 and 1. When we try some values between the right of 1, between minus 1 and 1, in the left of 1, we conclude this. That's why we can talk about the concavity. It's upward when x is less than 1, and it's downward when x is the concavity is upward when the second derivative is positive. بمعنى in the right when x is more than 1 and x is less than 1, and it's downward here between minus 1 and 1. Maybe this is all. Now it's time to put all together in the graph. طبعا بالنسبة للرسم نحاول نستعمل كل النقاط، كل المعلومات اللي معنا، وإذا احتجنا لبعض النقاط نزود بعض النقاط. Here we said we have a problem. We have the three verticals, two verticals asymptote and one horizontal asymptote. Okay, what is the situation between negative infinity and minus 1? Your function is increasing. Okay, we have your function goes to 2 when x goes to negative infinity. بمعنى تيجي من 2 تصعد إلى infinity. This is related to the left side. Between minus 1 and 1, in minus 1 it's negative infinity, and in 1 it's negative infinity. In 0 it's 0. Then we have increasing and decreasing. We try to draw something like that. And finally, in the right of 1, it's not defined in 1. In the right of 1, we use the symmetry, for example, or what you want, in order to draw something like this. Is all about this example. We can look the example 2 as in YouTube in order to understand better. This is all for chapter 4. It's done. I don't know if we have any question. في سؤال.